a question about free body force diagrams. So figure 1 shows an aircraft flying at constant velocity and a constant height above the ground. So constant means staying the same. Velocity is speed and direction. So this aeroplane is flying forwards, constant height above the ground, not changing its speed and not changing its direction. So Newton's first law tells us that things going at the same speed in the same direction have balanced forces acting or zero resultant force. So we know the forces acting on this aircraft have to be balanced. And the question asks us, complete the free body diagram in figure 2 to show the other two forces acting on the aircraft. So a free body diagram is just when physicists are too lazy to draw a plane or not good at drawing. So we simply draw a dot to represent the aircraft. And we show the forces acting on it using arrows. So the length of the arrow tells us the size of the force, and the direction of the arrow shows us the direction of the force. So we can see from this diagram that the drag force acting backwards on the aircraft, so that will be due to air resistance, is bigger in magnitude or size than lift. And they're not acting in opposite directions. One's acting up and one's acting to the right, so they can't balance each other. So we need two more forces, one that's going to be balancing the lift force and acting downwards, and the other that is going to be balancing the air resistance force and acting forwards. So, because they're balancing, they need to be in opposite directions and the same size as the force they are balancing. So that's what our two force arrows should look like. And you'll also notice on this diagram that they've labelled the names of the force. So lift is pointing upwards. So the force that's acting downwards on the aircraft we know is going to be the weight force that's pulling it down towards the centre of the earth. So you would need to label that weight, and the arrow pointing to the left or the forwards is going to be called the thrust force. So that's due to the engine. So we'll label this one thrust, and this other one gets labelled weight. So it's really important that you get the length of those arrows to match the ones that they are balancing. And it's really important that you remember to label them and that you show the direction of the arrow. So there's quite a few things you have to do to actually get those marks. Next part of the question, a small aircraft accelerated down a runway at 4 meters per second squared. So it's taking off. Accelerate means it's increasing its speed. The aircraft started from rest, so that means it was stationary, not moving, and reached a speed of 34 meters per second just before takeoff. So that's how much its speed has increased. Calculate the distance travelled by the aircraft while it was accelerating. So this equation is on the equation sheet. It's mentioning acceleration, speed, and distance. So those three things make us think of this equation and choose this one. So I've written out the equation in symbols. So it's final speed squared, take away initial or starting speed squared, equals 2 times acceleration times distance. They use an S for distance, which is a bit confusing. So we need to work out what the values are we've been given. Acceleration, we can recognise meters per second squared is the standard unit for acceleration. So that value of 4 is A. Starts from rest. So start means initial. Rest means not moving. So initial speed is U is 0. And reaches a speed. Meters per second tells us it's a speed. Reaches it tells us it's the final one. So that's V equals 34. And distance, S, is what it's asked us to calculate. So the first thing we need to do is substitute the numbers that we've got into the equation. So 34 squared, must not forget those squares. Take away 0 squared equals 2 times the acceleration is 4 times the distance is S. And then 34 squared is 1,156. Take away 0 is still 1,156. Equals 8, which comes from the 2 times 4, times by s, which is what we're trying to find out. So we need to rearrange this equation to get our answer for s. So remember, the rule is that the thing that is on its own on one side of the equals, in this case that 1,156, goes on top of the division. So it starts on its own on one side of the equals, it ends up on top of the division. So we're doing s is 1,156 divided by 8 gives us 144.5. And I would strongly recommend then that you type in 8 times 144.5 and check that you get 1,156. Then you'll know you've rearranged it correctly. So that is the distance, but the thing we mustn't forget is it says give your answer to 2 significant figures. So this is 4 significant figures at the moment, so we need to round it to 2. 4.5 is less than 5, so we're rounding it down, and we come up with 140 metres is our correct answer to 2 significant figures. The final part of this question, figure 3 shows the small aircraft being used to tow a glider. A glider is just a plane without its own engine. So we've got a cable and a tension force acting down and to the left. It's always important to think about what direction the forces are in. The tension force in the cable can be resolved into a horizontal component and a vertical component. So that means we consider this tension force is kind of dragging it a bit down and a bit to the left, and we want to separate it out into the bit that's acting to the left, which is horizontal, and the bit that's acting down, which is vertical. The tension in the cable is 2,000 newtons, so that's the overall effect or resultant of pulling it down and pulling it to the left. The cable makes an angle of 20 degrees with the horizontal. Draw a vector diagram to determine the magnitude of the 2 components of the tension force. So magnitude, that just means find the number of newtons acting down and the number of newtons acting to the left separately. And draw a vector diagram, that's going to be drawn to scale. And that means we're using arrows to show our forces, with the length of the arrow showing us the magnitude or size, and the direction of the arrow show the direction. So it makes an angle of 20 degrees, so I need to use a protractor. So the first thing I'm going to do is just draw in a horizontal line, because it says 20 degrees with the horizontal. And then you can see I've lined the middle part of the protractor up with the far end of my horizontal line, and I've used that protractor to draw in a line that's at 20 degrees to the horizontal. So I've got the direction of my tension force, my resultant force. I now need to get the magnitude, or think about how long that arrow's got to be to represent 2,000 newtons. So that means I need to come up with a scale. So I'm going to say 1 centimetre equals 200 newtons, therefore my 2,000 newton force is 10 centimetres. So I'm going to extend that line out until it's 10 centimetres, and I'm going to put an arrowhead on it to show the direction that it's pointing on. And I could put that in the middle of the line. Now, obviously, you have to adjust to the amount of space that you've got. You might find 10 centimetres doesn't fit, in which case you might go down to 5 centimetres, so 1 centimetre is 400 newtons. And then we've now drawn our resultant to scale. So we've drawn a vector diagram of this tension force, and we now need to find the horizontal and vertical components. Okay, and that just means drawing in arrows like that. So pointing down from one end of my 10 centimetre line to the other end, down and across, making a right angled triangle. And again, it's important to draw arrows on those to show the direction. So this one is down, not up. and this one is left, not right, because the glider is being pulled down and to the left. Now I need to find the magnitude in newtons, so that means I need to measure the length in centimetres and use my scale to convert that into newtons. Okay, so basically you are measuring how many centimetres long your line is, and you're timesing it by 200 because our scale is 1 centimetre equals 200. And the final answer you should come up with is the horizontal is 1900 newtons, so that should be about 9.5 centimetres long, and the vertical component is 680 newtons, so that should be about 3.4 centimetres long. They do give you a range. It was between 1850 for the and 1925 for the horizontal, between 660 and 700 for the vertical, if you want to actually have a go at drawing that scale diagram yourself.